Okay, so for the next 3 lessons, we're going to be learning about some rules that we use for non-right-angled trigonometry. Now, this is something that only those in the top maths class from year 10 would have seen before, and even then, sometimes it's a bit confusing for those classes. So, if you're not quite sure about it, make sure you spend your time with it. But there's going to be 2 videos here. This video is a non-compulsory one. It's up to you if you want to watch it, and this goes through why the sine rule works. The other video, which will be compulsory, is dealing with how we actually use the sine rule, and we'll go through the lessons. So if you're interested in following this, if we go past all the lessons, down the bottom here I'll have the proof non-compulsory. So if you jump into that, we'll go through what the proof is. Now, it's quite standard when we create a triangle to pick some letters to give the triangle a name. So this is triangle ABC, and we always use big letters. Angles are represented by capital letters, and lengths are represented by smaller letters. So what we might just do is get in this idea first of, well, the side that's opposite angle A is going to be side little a, and the side that's opposite angle B is going to be little b, and the side that's opposite angle C is going to be little c. So there we've got triangle ABC, and there's its 3 sides. Every side is effectively opposite the angle for which it's named. Okay, and then with this particular one, there's no 90-degree angles. We can't use any of the trigonometry we were using before. There's no 90-degree angles there. But of course, any triangle like this, if I drew a perpendicular line from, say, this length AB up to the point C, I would not only create a 90-degree angle, I'd create 2 right-angled triangles. So just in relation to this, I'm going to call this one the left one, and I'll do stuff in blue for that side, and I'm going to call this one the right one, and I'll do stuff in green for that one. So if I was interested to find out, let's just call this point here E, where we've the point where we've made that line. Let's call that E. So if I was going to find the length of CE in this left-hand triangle, obviously I've got a right-hand triangle, that left-hand triangle. So the length of CE, I'd be interested in, because we're using sine, we know it's the sine rule, we'll be interested in the hypotenuse, and we'd be interested in the opposite side. So if I said sine, obviously we know that sine theta equals the opposite over the hypotenuse. Now, in this particular case, we fill in what we know. So sine, and that angle is A, equals the opposite. Well, the opposite is that line CE, and the hypotenuse is that line B. But we know that CE is common to both triangles. So let's just move this around. If I multiply both sides here by B, I'm going to end up with B sine A equals CE. Okay, so I know that I can get using the left-hand triangle, I can get a expression that basically equals that length of C, and that's B sine A. And that's just using what we already know from right-angle trigonometry. But if I try to then, using the right-hand triangle, if I try to find the length of CE, once again I use sine theta equals the opposite, that's a bit big, the opposite over the hypotenuse, and in this case we're going to use that angle B. So sine B, if B is the angle we're interested in, the opposite is that side CE, and the hypotenuse is that side A. And once again, if we multiply both sides by A, we're going to get CE on its own. So we're going to end up with A sine B equals CE. So now we've got this situation where both of these are equal, both of these expressions are equal to CE. So if they're both equal to CE, then they must both be equal to each other. So we can therefore say that B sine A equals A sine B. Now, we could use the sine rule just like that, but we kind of like the idea of having the A's and the B's together. So if we divide both sides here by A, then we're going to end up with b sine a over a equals sine b, and then we'll divide both sides by b. So I'm going to divide by b on this side, I'm going to divide by b on this side, and I will end up with sine a on a equals sine b on b, which is our sine rule. Of course, remembering that if we flip that upside down, it's still going to equal the same thing. And we can use that same basic setup to also prove that that is also equal to sine c on c. We would create a 90-degree angle up to point B there and work it out that way from that line. But yeah, that's essentially the basic theory behind why the sine rule works. Essentially, in order to prove the sine rule, we just split a non-right angle triangle into two right angle triangles, and then we use what we know about right angle triangles, and that creates this rule. And you'll notice with that I didn't use any numbers, so this will work for any numbers, any values of A and B, and C obviously for the other angle. And that's the proof of the sine rule.